Hey, let's take a look at an example of how you can generate electricity using a rotating loop. Um, this is how you can generate what's called AC electricity. AC stands for alternating current. So let's take a look. I'm going to read the description of this at the top of the page here. You can follow along with the handout. It says the rectangular coil shown has n turns. An external torque causes it to rotate at uniform angular velocity omega, clockwise about the positive x-axis. The loop lies in a uniform magnetic field which points in the direction of the positive y-axis. At time is equal to 0 seconds, the loop is in the orientation shown in the figure. So just kind of take a moment and get familiar with the different axes, right? So your positive x-axis is this one here. Positive y is kind of coming out at us, and positive z is going straight up. Okay, so this loop is starting off in the xz plane. Okay, can you see that? And so its area vector, the area vector that it starts with, is going to be the vector that's perpendicular to the loop. That's going to stick out in the positive y direction. And so I hope you can see that the area vector is going to line up with the magnetic field from the outside. So let's do this. Let's make some sketches in part A. And we're going to sketch the area vector of the loop and the magnetic field vector from the outside. And we'll just see what those look like. So in the sketches here, what it might help you to do is to just kind of do this. We're going to put positive y pointing to the right, and we're going to put positive z going up. Okay, and so what does that mean? That means that positive x would be pointing out at you, and I'm not going to draw that. Okay, but you should understand that positive x is coming out at us. Okay, so the first thing we're going to do is kind of sketch the orientation of the loop at t is equal to 0. And I'm going to make this a little bit wider here. So the loop is actually kind of, if you look at it from the side, it's like that, right? You're just seeing the edge of it. And so let's go ahead and let's then sketch the area vector for that loop. That's going to go this way. I'll label that A. That's my area vector. And then the magnetic field, which is coming from the outside world, is going to be, of course, going in that same direction. So this is the B vector. All right, so that's kind of the starting point for this. Now, what we want to do with a problem like this is say, well, what happens if this loop rotates? Okay, if it rotates clockwise in this picture, what's going to happen is that the flux through the loop is going to change. And what we want to do in this problem is relate the rate at which the flux changes to some type of an EMF that we can generate. Okay, so that's what we're going to do. So let's go ahead and let's do the rest of the sketches here. I'm going to just go ahead and draw axes across. Something like that. And what you'll notice here is that we're breaking this down into fractions of the period that it takes for the loop to rotate around. So 1/4 of a period, 1/2 of a period, 3/4 of a period, and 1 full period. So what I'm going to do, the first thing is, just so I really understand this, is I'm just going to sketch like the orientation of the loop. The loop is going to rotate clockwise, right? So after 1/4 of a period goes by, the loop itself is going to be going this way. It'll be kind of like in the XY plane. After 1/2 of a period goes by, it's going to rotate. It'll be back around upside down. 3/4 of a period brings it back this way. And of course, 1 full period later, we're back to where we started. Okay. So let's go ahead now and sketch the area vectors that go with those situations. So you're going to have an area vector that points down. Then the area vector is going to be pointing kind of backwards. And then the area vector is pointing up. And finally, it comes back around to where it was originally, which would be here, okay? So again, the loop is rotating in the in the clockwise direction when we look at it this way. All right, the magnetic field is always going to be the same. So the B field, right, is always the same. So that's going to be B for all of these, right? And so I think, and I hope you can see that what's going to happen is you're going to get, the flux is going to be changing as you go. So what I'm going to do is there's not a lot of space up here, so I'm going to kind of come straight down. And I can see right away that in this first picture, there's going to be a positive flux through the loop. Lots of it, right? Maximum amount. And then in the next image, I can see that the loop is kind of like the area vector is perpendicular to the magnetic field. So there's zero flux here. At 1/2 period, you're going to have negative flux because now the area vector is pointing in the opposite direction of the magnetic field. Back to 0, and finally back to positive magnetic flux, maximum value. Okay. So what you have, if you were to make a graph of this, is you'd see something like this. Let's try to graph it out. So we'll have a really long, stretched out, skinny graph. But you would have something, let me get this here. We're starting off with some positive value up here. This is going to be flux versus time. So it starts out positive, it drops down through 0, goes to some negative value, comes back to 0, comes back to positive. And I hope you can see that it's following kind of this pattern, which is a cosine function. Okay, that's a cosine function. So I think at this point we're probably justified in just writing that. So underneath here I'm going to write an expression for the magnetic flux, and that's going to be equal to this maximum flux that you can have, right, which is coming from multiplying A times B, or B times A, times the cosine of some kind of function, right? So the B times A is giving you the biggest flux you're ever going to have, right? And of course, that's when the area vector and the magnetic field are lined up. And we see that at time is equal to 0. We also see that at time is equal to 1/2, except it goes the other way. The other thing we throw into the equation here, so we've got that out in front. That's kind of like your that's like your limiting value, or not your limiting value, but your amplitude of the cosine function, right? B times A. And then in the argument, you're going to have something that involves t, and we are told that this loop is rotating with an angular frequency, omega, right? That was part of what we were told. So that's the function that you have for the flux. It changes with time. It changes with time. And that's what we want to get, right? So this is an easy thing to set up. Like, practically, you can make a loop and you can spin it inside of some magnetic field to make the flux change. All right, so then we're going to, of course, we want to know, well, how much EMF is induced in the loop. So we have to use Faraday's law. So we start off by writing it down. And then you substitute your function in for the flux, the magnetic flux. So this is negative derivative with respect to time of this function, right? Of the function B times A times the cosine of omega t times all that. And of course, B and A are constants here. So they come out, so you're going to end up with negative B times A. And when you take the derivative of the cosine function, what you end up with is the negative sine function, right? That's something you should know. And the omega is a constant, and so that pops out. So taking the derivative of this cosine omega t leaves you with this. It's going to leave you with negative sine, whoops, left something out there. Leaves you with negative omega times the sine of omega t. That comes back. So make sure that you're able to do that and without, that you understand where that's coming from. And so then what that gives us is going to be the two negatives cancel. And so you have B times A times omega times the sine of omega t. And that's positive. Okay. And sometimes what you'll see is so this is important, right? That's a nice result there. Sometimes this will be written in the following way. You would write it as the EMF is equal to like some kind of a maximum EMF times the sine of omega t. And that's where E max, right, that's going to come right from this formula up here. That's just equal to BA omega. Okay, so you might see it this way. But the important thing is that, you've got that type of a, relationship. So a cosine for the flux becomes a sine for the EMF. All right, now you have a paper copy of this, and so let's take a look here at what comes next, because this is kind of interesting, because this gives you a nice kind of three-dimensional view of what's going on with your loop as it rotates. And what you're going to see first of all is, remember that our flux, this is the flux right here, this kind of reddish curve, this one, that's your cosine, okay? And then this other curve, the blue one, or we'll make it dashed, that's actually the EMF that you're getting. That's the sine function. So those are the two functions we just derived. And what you'll see, this is sort of interesting, is think about it like, think about the solid curve, right? That's the flux. Look down here. This is a point where there isn't much change happening with that function down here where I put a dot, right? Because it's kind of a place where the slope is equal to 0. So there's no change that's happening right at that instant. And if there's no change in flux, check it out. You have an EMF of 0 at that point. So this is where you have no change in flux. And that's the turning, it's like a turning point in the flux function. It's a turning point in the cosine, and that's where there's no EMF. If you want to contrast that, look at a place where there's a lot of change in flux. Like, for example, look here. That's kind of where you have a big change in the flux, right? The flux is increasing most rapidly. And as a result, you're going to have the largest EMF right here. It's a big EMF, okay? The EMF is negative here, right? Because this change in flux is a positive change. The slope is positive. And I hope you can see that it also happens over here, where the change in the flux is negative. Flux is decreasing most rapidly. That's where you have your biggest positive EMF. So that's important that you kind of see and can understand the relationship between the two graphs. Okay. So there you go. There you have it. What else do we have here? We've got that. Let's take I'll let you work out a problem or two, and just to see if you can do these. E and F are both things that you can check out. One thing I will point out, and oftentimes in problems, is you have more than one turn of wire. Like if you have 500 turns, what happens with that? Well, essentially what that does is it just adds that N term to your Emax, your maximum EMF. So remember before how we said that Emax was equal to B times A times omega? Well, now we're actually going to throw in the number of turns out in front, okay, to make that work. One thing I'll point out here is that when you use this formula, you absolutely need to express omega in radians per second. Absolutely. Okay. And that allows you the units to work out for other things here. Okay. Because what you want to end up with are units which end up being volts. So I'm going to let you try this one, part E. At the end of the day, you should be getting a 12 volt maximum EMF. And basically the same kind of formula, same kind of approach for part F. And the trick here is you're going to have to convert your rotations. You're solving for omega, okay? So you can rearrange the formula up above. But when you get an answer, I want you to convert it into rotations per minute. And you can check it, and you should get 690 rotations per minute. So you got to take radians per second, right, from the formula, radians per second, and you got to convert them into this. So solve for this, solve for that, but then convert it. All right, so that's about it. You can show your teacher when you have those two things, but that's kind of an overview of AC generators and how they work.